Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, just 4 days ago. It demonstrates a new technique that improves reasoning accuracy on the challenging GPQA Diamond benchmark by 11% compared to supervised fine-tuning, doing so without ever updating the model's main weights. The paper is titled ReasonCache, Teaching Large Language Models to Reason Without Weight Updates. And as we'll see later, the results are really impressive, especially regarding the efficiency gains over traditional methods. Figure 1 illustrates the core difference between ReasonCache and existing approaches. On the far left, in-weight learning updates the model parameters themselves, shown in pink. In the middle, in-context learning keeps the model frozen, but adds examples to the prompt, which consumes the context window. ReasonCache, in the third diagram, takes a middle path by learning a fixed key-value cache directly at each layer, while keeping the backbone frozen. The chart on the right shows the result. ReasonCache achieves over 42% accuracy, clearly surpassing both supervised fine-tuning and standard in-context learning. While Figure 2 expands the evaluation to 4 additional benchmarks, revealing 2 distinct patterns. On the left, looking at the AME math competitions, we see a case where standard fine-tuning methods, shown in blue and purple, actually hurt the model compared to the green baseline. ReasonCache, however, represented by the red bars, successfully preserves the model's original strong performance. Then, shifting to the GSM-8K and math datasets on the right, the method demonstrates massive improvements. In these cases, ReasonCache dramatically outperforms the in-context baselines and matches or even beats full supervised fine-tuning. So, having seen the final accuracy scores, Figure 3 reveals precisely how data efficient these methods are. The chart plots accuracy on GSM-8K, distinguishing between a purple low data zone on the left and a yellow high data zone on the right. In the purple phase, the orange in-context learning line rises quickly, but it abruptly crashes to 0 as the context window overloads. In contrast, the red ReasonCache line matches that start but keeps climbing steadily into the yellow zone, consistently staying above the blue LoRa curve. This effectively bridges the gap, combining the fast start of prompting with the robust scaling of fine-tuning. Alright. While the previous chart focused on data efficiency, Figure 5 examines inference behavior on the complex GPQA Diamond benchmark. The bar chart on the left highlights a trade-off. Supervised fine-tuning, in the middle, boosts accuracy but drastically increases response length. In contrast, ReasonCache reaches the highest accuracy, over 42%, while keeping responses 34% shorter. The diagram on the right illustrates why. It suggests fine-tuning forces the model to unpack strategies into verbose text, whereas ReasonCache stores that knowledge efficiently in the prefix, enabling a more concise thinking phase. Okay, distinct from inference costs, Figure 6 compares parameter efficiency directly. The chart plots test accuracy on GSM-8K against the number of trainable parameters on a logarithmic scale. The blue line shows LoRa, which starts strong but eventually hits a ceiling, saturating near 52% accuracy. In contrast, the red ReasonCache curve remains consistently higher at every single budget point. Crucially, it avoids that plateau and keeps climbing as more parameters are added, showing it can use extra capacity far more effectively. Well, Figure 7 provides the theoretical explanation for that efficiency gap using a geometric analogy. Panel A shows the base model's representations confined to a vertical line representing a limited low-rank context. In the middle, Panel B illustrates low-rank adaptation. Even with high-rank adapters, the update is constrained by the input data's rank, a limitation the authors call the carrier bottleneck, so it can only expand into one new direction here. Finally, Panel C shows prefix tuning. By injecting independent vectors directly into the attention layer, it spans the full horizontal plane, accessing a much richer subspace that weight updates simply cannot reach. So moving to Figure 17, we see the hidden cost of that supervised fine-tuning. These charts track the base Llama 2 model in red against the fine-tuned version in blue across 3 general benchmarks: Trivia QA, PIQA, and Hella Swag. The drop in performance illustrates catastrophic forgetting. On the left, Trivia QA accuracy collapses from over 50% down to single digits, just because the model was tuned on math data. The other tasks suffer too, showing that weight updates damage general knowledge, whereas ReasonCache avoids this completely by leaving the original parameters untouched. Wrapping up, ReasonCache establishes a powerful middle ground between prompting and fine-tuning. It proves that fixing the weights and optimizing the cache offers better efficiency and expressivity than even popular methods like LoRa. This could fundamentally shift how we modularize and deploy reasoning skills in future systems. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.